So, let us start our third class on TP. In this class, I will try to make you understand that how the problems related with the dimensional analysis can be taken care of and how such an analysis enable you to correlate the different situations on the basis of such a relationship. Let us suppose you are analyzing a physical phenomena and you have arrived at a certain dimensionless functional relationship among the pi groups which are involved in that particular physical problem. Many times you will find that those functional relationships match a lot with the existing principle. So, basically there are two types of numericals or two types of practical problems associated with dimensional analysis. One type is where the number of relevant variables associated with the physical phenomena are such that through the inspection you can easily derive that what are the pi groups which may be involved in that process. Second type of problem is there where you have to conduct the dimensional analysis by utilizing the Buckingham pi theorem to arrive at the different pi groups associated. Many times the problem is of nature that you have obtained a dimensionless relationship or functional relationship among the pi variables, pi groups. Then you have to compare that equation that you have obtained with the existing relationship associated with that particular physical phenomena. You will find that those earlier arrived that relationship between those variables matches 100% with the dimensional analysis results. So, I would like to make you able to understand the different types of problems associated with the dimensional analysis in today's class. So, let us go one by one such type of problems. Because of the fact that this paper is basically very mathematical in nature, so every time you have to pay emphasis on the numerical problems. So, let us try to solve some problems related with the dimensional analysis. So, the name of the topic for today's class is dimensional analysis problems. Here I would like to suggest you that the book written by Bird, Lightfoot and that I have given in the previous classes, that book contains a lot of problems related with this kind. So, you should go through that book in order to have a better understanding of the dimensional analysis, not only the dimensional analysis, but also have a better understanding of all the numerical problems related with the transport phenomena. So, the question number 1 is the mass transfer coefficient, the mass transfer coefficient of a component this is abbreviated as K suffix m depends upon density rho viscosity mu, velocity of fluid v, diffusivity of the component. This diffusivity of the component is denoted by letter capital D and characteristic distance small d. Use the dimensional analysis. Use the dimensional analysis for arriving at the functional relationship. This is the problem that you have, and you have to apply the principle of dimensional analysis to solve it. Here you can easily see that the number of relevant variables, here in the present problem are, what are those relevant variables? First is the mass transfer coefficient of the component, that is the Km, density of the fluid, viscosity mu, velocity of the fluid v, and diffusivity of the component under consideration. That diffusivity, that means what is the rate of the diffusion of that particular substance through unit cross section in unit time. So, diffusivity and the characteristic distance d. So, these are the 6 variables associated with this problem. Fine. In order to solve such type of problem or any type of problem related to the dimensional analysis, it is advised that in a tabular form you should first write the dimension of each of the variable. So, here the variables are, so if I am tabulating here, so the variable here is the dimensions. So, the first variable is Km, that is the mass transfer coefficient. So, the mass transfer coefficient has a dimension L t to the power minus 1. Second variable is the density, the dimension is m L raised to the power minus 3, mu, that is the coefficient of viscosity, m L raised to the power minus 1, t raised to the power minus 1, v, that is the velocity, that is the L t raised to the power minus 1, d, that is the diffusivity, this has a dimension L square t to the power minus 1, and the characteristic distance must have the dimension of the length. So, these are the dimensions of all the relevant variable associated with the present problem. Now, see, out of these 6 variables, you can easily see the dimensions or the variables which cannot be grouped together to form a pi group. This is a thing that which requires a lot of practice where you can easily assess that okay, these are the different parameters or different associated variables which cannot be grouped together to form a dimensionless group. So, if I would like to emphasize the name of those variables which cannot be grouped together here to form a pi group. So, here the variables are mu, diffusivity d and the characteristic distance d, small d. These variables cannot be grouped together to form a pi group or dimensionless group. So, these variables are called, so these variables can be regarded as the primary variables here. Similarly, similar to the case that the mass, length, time, the luminous intensity, the amount of substance, the electric current, these variables cannot be grouped together. So, those variables are called the fundamental dimensions of primary variables. Here, so far as the grouping of those dimensions are concerned, so we are selecting here the primary variables in terms of the variable which are given in the present problem. Now, here utilizing the Buckingham pi theorem, here by using the Buckingham pi theorem, that is the scale variable 1 raised to the power a, scale variable b 2 raised to the power b, and so on, you can easily obtain the pi group. Because of the fact that I would like to emphasize here that a different way to tackle the dimensional problem. So, I am solving here by inspection mode, through inspection mode. Here, if the three variables cannot be grouped together to form a pi group, so the number of pi groups which can be generated here, because the total number of variable is 6, here total number of variables is equal to how much? 6, and primary variables are 3, primary variables are 3. So, the number of pi groups is equal to 6 minus 3 is equal to 3. So, let us arrive at those pi groups. So, this quantity and this quantity are regarded as the primary variables. So, the rest variables are km, rho and v. Through the inspection mode and through the adjustment methodology, we will arrive at the different pi groups. Now, take the first variable km, taking km. So, let us suppose number A, taking km, that is the mass transfer coefficient. What is the dimension of km? Km has the dimension is equal to Lt raised to the power minus 1. That can be it can be further written as L square t to the power minus 1 divided by L, is it not? L square t to the power minus 1 stands for the dimension of the diffusion coefficient. So, this is d. L stands for the dimension of the characteristic distance. So, this is equal to d. So, km is equal to d by d. Hence, the first pi group which is possible here, the first pi group which can be possible for the present case, km is equal to km into d, which is small d divided by capital D, km into small d divided by capital D. This is the first pi group that we have obtained. Now, taking the second variable, taking rho. Now, the rho has a dimension ml raised to the power minus 3. It can be written as ml raised to the power minus 1 t raised to the power minus 1 divided by L square t to the power minus 1. Okay, this L to the power minus 3, this should get considered ML raised to the power minus 3. This stands for the dimension of what among the various variable, that is the mu divided by this, that is the diffusivity. So the second pi group associated with this problem should be rho d divided by mu. Let it be question number 2. Now taking the last one, that is the velocity. Taking v, that is equal to L t to the power minus 1, that may be written as L square t to the power minus 1 divided by L. So L square t to the power minus 1 is equal to d divided by small d. So the third pi group associated is v d upon d. So the functional relationship may be, hence the functional relationship may be relationship may be, that may be pi 1 is a function of pi 2 and pi 3, or you can write here kmd upon capital D, that should be equal to function of this rho d by mu and v d by v small d upon d. So this is the functional relationship which I had to obtain in the present mathematical problem, present problem of the dimensional analysis. This is the one type of problem. Now the second and third type of numerical problem that I have stated earlier, that will be reflected in the second problem that I am going to solve in the present class. The second problem is obtain a non-dimensional form of expression for pressure gradient in horizontal pipe of circular cross section, second part of the problem will reflect the third type of problem, that you have obtained a non-dimensional relationship among the pi group for a physical problem, and you will find that this equation resembles, this relationship resembles with the earlier established relationship by some other authors. So, it is necessary to validate your way to arrive at that particular relationship through the dimensional analysis. You can easily check that whether the pi group that you have obtained, whether the pi groups are correct or not. So, also the second part of the question is also so that how it relates to Darcy-Weisbach equation, the equation that I have given you the reference in the previous classes, Darcy-Weisbach equation for frictional head loss. In such type of problem, here it is necessary to extract the what may be the different variables associated with this problem. So, our first task in such type of problem is to identify the variables and their respective dimensions. Variable dimensions variables and dimensions. First variable may be the pressure gradient dP upon dx. What should be its dimension? Pressure, the force per unit area, that is the ml t to the power minus 2 divided by L square, and the dimension of dx is L, that is the length dimension, that is equal to m L to the t to the power minus 2 t to the power minus 2. So, here I have to also incorporate, so write the dimension directly here, ml raised to the power minus 2 t raised to the power minus 2, ml raised to the power minus 2 t raised to the power minus 2. Another variable is rho, that is the density, ml raised to the power minus 3. Here another variable is v, that is the velocity, the dimension is L t to the power minus 1. The characteristic distance or characteristic length, these are the dimension L. The other variables may be the surface roughness, this is denoted by a symbol Ks, its dimension should be L, and the viscosity that is denoted by mu, the dimension is ml raised to the power minus 1 t raised to the power minus 1. See, when a fluid flow through a conduit, flow through a pipe, the nature of the protuberances on the inside layer, inside periphery of the conduit gives rise to a reduction in the pressure, reduction in the velocity, hence the reduction in the pressure. Now, utilizing the well known Bernoulli equation, the total energy at a particular cross section, the total fluid energy will be constant. So, in order to adjust this change in the velocity, the change in the pressure is also there, and correspondingly the head loss will also get changed, that is the amount of head also got changed. Such type of phenomena is what is known as the Darcy phenomena. So, the roughness gives rise to a reduction in the velocity, hence the reduction in the pressure, and hence the reduction in the pressure head. So, the surface has a major role to play in such type of flow behavior, and because of the fact that at any of the surface, if you examine any surface microscopically, that if a surface, let us suppose this is the circular surface, this looks flat, but once you start the examining this surface in a microscope, you will find that there are so many protuberances or undulations are there on the surface of different height. This gives rise to the creation of surface roughness. This surface roughness has a great role to play in order to decide the bearings in the automobile that we are using. The wear and tear of the bearing depends a lot on that protuberances or the undulations on the surface. So, here the number of variables is equal to 6, independent dimensions 3, independent dimensions is equal to 3, so number of pi groups possible is equal to 6 minus 3 is equal to 3. Now, taking or choosing now scale variables. What I have told earlier in the previous class, that one choice can be made as choosing a purely geometric quantity. The purely geometric quantity may be here the characteristic distance d, one purely kinematic quantity v, and one kinetic quantity rho as scale variables, taking as scale variables. Now, we will conduct the dimensional analysis now. Okay. So, because of the fact that the number of pi groups possible is 3, so let us subdivide this area in 3 parts for a better insight. So, the first group, according to the Buckingham pi theorem, that is the pi 1 is equal to one first rest variable, that is the dp by dx, d raised to the power a, v raised to the power b, rho raised to the power c. Is it not? This is the fundamental of Buckingham pi theorem. So, pi is a dimensionless number, so its dimension should be m raised to the power 0, l raised to the power 0, t raised to the power 0, that should be equal to t raised to the power minus 2. Dimension of d is l raised to the power a, lt to the power minus 1 raised to the power b, m l raised to the power minus 3 raised to the power c. So, that will be equal to m raised to the power 1 plus c, l raised to the power minus 2 plus a plus b minus 3, and t raised to the power minus 2 minus b. So, the equations, so the 3 variables are there, a, b and c, corresponding to 3 linear equations you have. 1 plus c is equal to 0, minus 2 plus a plus b minus 3 c is equal to 0, minus 2 minus b is equal to 0. It gives rise to the value b is equal to 2. b is equal to minus 2, c is equal to minus 1, and a is equal to 1. A is equal to 1. So, the first pi group which may be generated is pi 1 is equal to dp upon dx d raised to the power a d v raised to the power minus 2 rho raised to the power minus 1, that is equal to d into dp by dx d into dp by dx divided by v square rho. This is the first dimensionless group which is possible for the present problem. Let us try for the second group, pi 2. Now, here you should apply some common sense here. Here you can easily see that the surface roughness and the characteristic distance both have the same dimension. So, pi 2 that is equal to Ks upon d, this is by inspection. So, your work has little bit been reduced. However, if you apply the Buckingham pi theorem, in that case as well you will obtain this group. You can see at your respective home that this is the second pi group that will be obtained here, utilizing the principle, this principle that I have discussed in order to evaluate pi 1. So, pi 2 equal to Ks upon d. Now, see pi 3. So, you have utilized k dp by dx, this I have utilized Ks by d, that is Ks I have utilized. Now, the left is mu. So, the pi 3 is equal to mu d raised to the power a, v raised to the power b, and rho raised to the power c. So, this will be m raised to the power 0, L 0, T 0, this is equal to m L raised to the power minus 1, T raised to the power minus 1, d L raised to the power a, L T to the power minus b, m L raised to the power minus 3 c, that is equal to m 1 plus c L raised to the power minus 1 plus a plus b minus 3c and t raised to the power minus 1 minus b. Okay. So, equating the indices for the principle of dimensional homogeneity, 1 plus c is equal to 0, minus 1 plus a plus b minus 3c is equal to 0, minus 1 minus b equal to 0. It gives rise to value a is equal to minus 1, b is equal to minus 1 and c is equal to minus 1. So, the third pi group is pi 3 is equal to mu divided by rho d v. Let it be question number 2, let it be question number 3. Thus, the functional relationship which can be assigned here, thus the functional relationship is pi 1 is a function of pi 2 and pi 3. So, we can write d into dp by dx divided by v square rho, that should be equal to function of ks upon d and mu divided by d rho v. Now come to the second part of the question. This is the dimension analysis obtained. So, your first part has the answer d dp by dx divided by v square rho, that should be equal to function of ks by d into mu divided by rho dv. Arrival of this result will complete your first part of the answer. If this question contains of 6 marks, that means up to this point you have done work for 3 marks. Now, the second part, which is slightly which requires some discussion in that. So, we have to proceed that part in a separate manner. So, let us try to go through the second part, that how also show that how this non-dimensional relationship matches with the Darcy-Weisbach equation for the frictional head loss. Now, we will proceed for the second part of the question, taking this relationship in view. So, let us suppose this equation as equation number 4. I will leave this equation number 4 and I will keep this equation number 4 for our ready reference for further discussion pertaining to the problem. So, the second part of the problem, here you have to write something. With respect to the obtained pi groups for the present case, if any of them can be raised by a power, that means either you raise the power raised to the power minus 1, raised to the power minus 2, raised to the power of 2, raised to the power cube. So, the very dimensionless group will not change. Dimensionless group, that means a group that may have the number 5 without any unit. So, if you are cubing it, it is 125 again, it is a dimensionless number. If you are saying 5 raised to the power minus 1, 1 by 5 again dimensionless number. So, it hardly affects what I am saying here. So, with respect to the obtained pi group for the present case, if any of them can be raised by a power, then number of pi groups can be kept intact, as well as the dimensionless nature will not change. So, taking the third pi group in consideration, the third pi group is pi 3 is equal to mu divided by rho v d. Okay. So, we can write here pi 3 raised to the power minus 1 is equal to mu divided by rho v d raised to the power minus 1, that may be written as rho v d divided by mu, is it not? What is this quantity rho v d by mu? That is inertial force divided by viscous force, and as I have told you earlier that inertial force divided by viscous force, it is a dimensionless number, that is called Reynolds number. So pi 3 raised to the power minus 1 is the Reynolds number. So the equation number 4, okay. Now evaluate this quantity dp by dx. Considering a column in which there is a liquid having the density rho, g the acceleration due to gravity, and hf, let us suppose this is the frictional head loss. So then dp by dx can be written as rho g h f divided by x as the dimension L. So rho g h f divided by L should be the value of dp by dx. L is the characteristic dimension, rho is the density, g is the acceleration due to gravity, and hf is the head loss due to the friction. So there is a rho g b hf by L. So we can write dp by dx divided by v square rho, that can be written as rho g hf divided by L v square rho. So that may be written as g hf d into, here d I am missing. So d into rho g hf divided by L v square rho, okay, dp by dx rho g hf by L into d, okay, v square rho. So this rho will get cancelled out. So d g hf d divided by L v square, okay. Hence relationship 4, relation 4 can be rewritten as d, that is the g hf d divided by L v square, that should be equal to function of ks by d, and this quantity may be written as Reynolds number raised to the power minus 1 or Reynolds number, because you are taking the function. So Reynolds number, or the expression for hf may be given as hf is equal to L by d v square by g into f ks by d Reynolds number. Now you have to write here, since that since numerical value or values may be observed in the non-specified, here you should write the equation number 5, non-specified function of equation number 5. Hence, this equation 5 may be regarded as similar to the Darcy-Weisbach equation, HF that is equal to F L by D into V square by 2G. That means keeping this factor half into this non-specified function. So, by doing so, this equation may be the equation that you have obtained through your dimensional analysis may be regarded similar to the well known Darcy-Weisbach equation for the determination of head loss in pipe flow problem. Thank you. In the next class, we will discuss the similarity criteria.